Okay, you guys have been playing around with the YouTube videos that I've been stocking for lectures, and in there you have had several on reactions for beams, so we're in beams. You have several that have how to figure reactions of various types of beams. You got some on internal forces, shear and moment. You played with that a little bit. And then you've got shear and moment diagrams. And then you had cross-sectional properties of the formulas. So we had formulas for stress. So we had stress formulas, FB and FV. And then we ended up with these equations needing some cross-sectional properties, and you had a little bit of time to play with those. So you know the letters that we were looking for were I, Q, B, and T, or B and C, excuse me. Some of them have the T in place of the B, so this is interchangeable. So what I thought I'd do is, since I've been online, hopefully you guys don't have too many questions about the concepts associated with that. I thought I would do a couple problems to try to pull all this stuff together and get us in a position where we finish Unit 2. And Unit 2, of course, was Chapter 2, which was axial forces and trusses, and Chapter 3, which is all this stuff associated with beams. Okay, on one of my links, I put a page 114 note on it. It's where the links were for several of the websites of YouTube. Make sure you know what page 114 does for you and says. I'm going to use it today, but it has common beams that we have in the world that have already been calculated by someone once. There's no use us recalculating things that we can find out fairly easily. So I'm going to start with one problem. We're going to do two in this lecture. They both have variations, so hopefully you'll see what the variations are. The first one I'm going to do is going to require us to draw a shear and moment diagram, but it's a relatively simple cross-section. It's a rectangle. The second one, I'm going to use page 114 to find the shear and moment, but the cross-section is not a very simple one. It's a T. So let's do example number one. Example number one is a beam that looks like this. It's a simply supported beam, has a roller and a hinge. It has a uniformly distributed load its entire length. And it has 3-point loads, and those point loads are at 4-foot centers. So I'm going to go to the middle, back half, and back half. So I got 1, 2, 3-point loads, and they are 2,500 pounds, 3,000 and 2,000. And they're 4 foot apart. And we've got a uniformly distributed load of 500 pounds per foot. And the cross-section is a rectangle that happens to be a piece of material that's 6 inches wide and 16 inches tall. Okay, the question here is, determine the bending stress and the shear stress in this cross-section. Maximum bending, maximum shear. So you had equations. You've already seen these. FB equals MC over I, and FV equals VQ over I, B, or T. Okay, there's our actual bending stress, actual shear stress. In the real world, we have to put an inequality here and put big F's there, just like we did before. Okay? When we did the axial, we had two sides. The left side, the big is the allowable, the little is the actual. Once again, these come from tables and books. They're calculated or figured out by American Society of Testing and Materials. They tell us what that particular material can carry. This case, we may be using wood, we may be using plastic, we may be using aluminum, doesn't matter. The process to get to stress is exactly the same for all materials. So let's take a look at it. What do I need? I need moment. M is moment. M max. You got two medias to get this from. Draw the diagram based on statics, or go to page 114. V is shear. Maximum shear. Same process. Statics, and draw the shear and moment diagram. This is going to be statics, means to draw the shear and moment diagram. Or go to page 114 and throw numbers into the equations and come with them. So that takes care of this guy and this guy. All the rest are cross-sectional properties. I, moment of inertia. Q, first moment of the area about the neutral axis, or the statical moment of the area. I, moment. V, we've got. B. B is the width of material at neutral axis. And C is the distance from the neutral axis to plane of evaluation. And we'll explain those, and hopefully you got those already. Those are something you should have had by viewing the YouTubes that I gave you to view. So we're going to have to populate those two equations. So how you populate them is up to you. If you want to do the cross-sectional properties first, that's fine. If you want to do the shear and moment first, that's fine too. On this one, I think I am going to actually do the cross-sectional properties first. They're pretty simple. Here's my cross-section. If I look at the beam, it's going to be 16 foot long. It would measure 6 inches wide and 16 inches deep. Here's the x-axis. And hopefully you can see that a rectangle, the center is the neutral axis. So if I do this, I can put 8 inches here, 8 inches here. And if I look at my picture now and relate it to those letters, letter B says it's the width at the neutral axis. That's there. So this is 6 inches. Okay, there's one of them. C, distance from the neutral axis out to the plane. The worst distance is C, is from the neutral to the outside edge. So if I go from here to here, it's the same as from here to here. That's 8 inches. I for a rectangle is given in your book. So if you go to the back of your text and you go to page 666, you're going to see a nice little table there. And in that table, the very first picture on the upper right left-hand corner is I equals BD cubed over 12. So for a shape like this, I is equal to BD cubed over 12. And if you look at that picture, B is the width, D is the depth. So it's 6 times 16 cubed over 12. So you take that and you run it through your calculator. Okay, 16 cubed times 6 divided by 12. 2048 inches to the fourth. Takes care of this guy. Now Q, hopefully out of the videos you got this, but I'm going to tell you how I do it. This is pretty simple. For Q, find the neutral axis. From the neutral axis crosshatch, either the top or bottom part of the shape. I'm going to do the top half. Okay, you want the moment of that area about the neutral axis. So if I draw that like this, and I get something that's got a little bit more juice to it. Neutral axis, shape. The moment of that area, area times distance to the center. So Q, area, distance, area 6 times 8. Distance to the center from the neutral axis. If I multiply those three numbers together, I've got the value for Q. So I've got 6 times 8 times 4, 192 inches cubed. Okay, there I am. I'm in good shape, so I'm going to go up there and get rid of some of these. 8, 2048, 192, 2048, 6. That leaves me what? 2 letters left. The maximum moment and the maximum shear. Okay, I take a look at this beam. It's got a uniform load. Unfortunately, it's not symmetrically loaded. My only option was page 114. You're not going to find a picture like that on page 114, or draw the shear moment diagram. I don't have a choice. My only option is draw the shear moment diagram. So I'm going to find the reactions. And I've got a roller. Get rid of that little guy and put an arrow there. I got a hinge. Get rid of that little guy and put a RY, RX, LY. Left hand vertical, right hand horizontal vertical. I'm going to sum forces into Y. I look at X. I have to consider X, but the only X up there is that RX, and that has to add up to 0, so that becomes 0. So I start right down the line, sum of the forces into Y. So I go up, LY is up, that's positive. 2,500, 3,000, 2,000, 16 feet times 500 pounds a foot, plus RY equals 0. So I take these and I multiply 16 times 500, 16 times 500 and get 8,000. I add 2,500, 3,000, and 2,000, 15,500. So the total of 15,500 pounds. Let's see if that looks good. 8, 10, 13, 15, 5 is perfect. Okay, my next job is to find out the reactions, and I'm going to go about the left-hand side. So I'm going to take and put a nail right here and watch it spin. 4 times 2,500 with the clock. 8 times 3,000 with the clock. 12 times 2,000 with the clock. 16 times 500 times 8 with the clock. Why 8? 16 times 5 gives me the area at X in the center, so it's going to be the 8 feet, and it's minus 16 RY. Okay, so let's do it. 4 times 2,500 plus 8 times 3,000 plus 12 times 2,000 plus 16 times 500 times 8. And I'm going to divide that by 16. 7625. And if I move that up into here, I end up with, actually I put it over here. I subtract that from 15.5. I get 78.75. Therefore, Ly equals 78.75. So I come over here and I put 78.75 right here. And I come over here and I put 76.25 right here. Okay, my reactions are done. I need to draw a picture that gives me a visual of what's happening from end to end. We do that by constructing our grid. Our grid, draw a line at the ends of the beam. Anywhere there's a reaction, anywhere there's a point load, and anywhere there's a change in load. First line is a horizontal line for shear. Second one is a horizontal line for moment. The graph